We want to now look at manipulating our binomial expansion to give us a few results. And so what we're looking at, we want to prove this result. And we've actually done this one, but it's just written a different way. But let's consider the binomial expansion and then show that this we can get this case. So if we look at 1 plus x to the power of n, is nc0, nc1x, nc2x squared, nc3x cubed, right through to ncn x to the power of n. Remember our notation for ncr there is we can write these in either way. So if we consider that expansion, if we let x be equal to 1, we'll put 1 in for x there, so 1 plus 1 there to the power of n gives us 2n to the power of n. And then we've got nc0, nc1 times 1, nc2 times 1 squared, and so on through to ncn times 1 to the power of n. Now, anything to the power of 1 to the power of anything is 1. So, basically, we can just write it as nc0, nc1 plus nc2, and so on through to ncn. And there's the result. What about the next one? Let's prove that, starting with our binomial expansion again, nc0 minus nc1 plus nc2 minus nc3 through to minus 1 n power of n ncn is equal to 0. So in this case, we're starting with our expansion again, but if we let x be equal to minus 1, we're going to get that result. So 1 plus minus 1 power of n gives us that result there. So, and notice we get the minus nc1 because we get a minus 1 there. Positive, a minus 1 all squared gives us a positive, but then you're going to get, it should be a negative there. Would be x cubed would be a negative, x and the x3 and the x power of 5 would be a negative, x power of 7 would give us a negative when we substitute minus 1 in. So in through to this one, we're not sure what n is, so we just have to leave it like that, minus 1 to the power of n, ncn. Next one's a little bit different again. We want to prove this statement. So nc1 plus nc2 lots of nc2 plus 3 lots of nc3 through to n lots of ncn is equal to n times 2 to the power of n minus 1. Now, when I look at this one, like the fact that I'm going to have an n minus 1 is a little bit of a hint for me what I want to do. Again, I'm going to start with this part here, and because I've got 2 lots of nc1, there's no nc0, so if the nc0 is going to go here, really the only way it's going to go is if I differentiate. So there's the trick to this one. To differentiate both sides with respect to x. So 1 plus x to the power of n gives us, by the chain rule, we get an n, bring the n down, 1 plus x to the power of n minus 1 times 1, and then we differentiate side. That's a constant, so it goes to 0. nc1x will derive the x, becomes just 1, so you get nc1. nc2x squared, bring the 2 down, times the nc2 is the number out the front, and x to the power of 1, subtract 1 from the power. So hopefully you're starting to see that it's starting to take shape. And because there's no x's there, how do we get rid of the x? Well, again, the 2 is a little bit of a hint there. So if we let x be equal to 1, we get the 1 plus 1 there, which gives us 2 to the power of n minus 1 there. And we put 1 in for x, 1 in for x squared, and again, like we've had before, adding 1 to the power of any number is going to be 1. So we end up with that result that we wanted. So there's the hint that I look for, like n minus 1 there, but also the constant terms gone from what we've started. Because we've got to start with this one, because that's what we know. We know that's true. This one's again a little bit different. So again, we're starting with that expression. How do we get to that one? Again, the hint I try and look for here is that I'm starting to see fractions. So where do I know fractions are going to come into play, especially from here, is if I start to integrate. Now, integration's a little bit harder because we're going to end up, when we integrate both sides, so 1 plus x to the power of n, add 1 to the power, divide by the power, times the coefficient of x, which is 1. But I'm going to get a constant of integration here. Now, integrate this side as well. You can see that integrate every separate term by itself. We're going to nc0x, nc1, x squared on 2, and so on. So what the problem is, it's going to be a constant. Now, notice I don't get a constant on this side. The only problem is, if we put a constant on both sides, well, basically, you're going to get constants on either side we could add and subtract them together to just give us a constant on one side. So that's why we only put a constant on one side of the function. So what we need to do is say, well, what's the constant going to be? So easiest way to do that is say, well, seeing if I put x is equal to 0 on this side, I get a whole bunch of zeros. Put a 0 in there, I get 1 plus 0, so just give me 1 to the power of m minus 1, so it's 1 over n plus 1 plus the constant. So our constant is minus 1 over 1 plus n. So that's our constant of integration. And we get our expression there, so the 1 plus x to the power of m plus 1 over m plus 1 minus 1 over m plus 1. So in this case, if we want to look at what we had before and what we need to find, notice we got a negative, a positive, a negative. So again, let's put a little bit of a hint to say, well, let's let x be equal to minus 1, because if we do that, well, we get 0 from that part. We just get a minus n plus 1, and then we've got an nc 0 times minus 1, nc1 times would be a positive a half, nc2 minus 1/3, and so we look at that and we notice we've got a negative here, so multiply everything through by -1, and it's going to give us the positive nc0, and then a minus half nc1 plus a third nc2, and so on through to minus n 1 over n plus 1, which is the last one, ncn, and a 1 minus 1 to the power of n. So there's the manipulations we can do. Either substituting numbers in, so in this case we had a 1 and a minus 1, or differentiating or integrating and then doing some substitutions to get the required expression. So it really, it's up to it gets a little bit of experience that tells you exactly what you need to do, but also like looking for things such as the fractions. That's always a hint that I find that tells me I need to probably integrate. And when I see something like that where the numbers are in front but it's sort of one more than what it should have been and the constant's gone, that's probably a hint that it's going to be a differentiation. So again, the more of these you practice with, the better you're going to get.